All right, here's example number 2 for a conservation of momentum. I'm going to give you a inelastic collision, and this is a demo that we normally do in class. So let me set it up for you. We have a air track, which is a long tube, like an air hockey table in a tube. Sorry, it's not very straight, but and then I have a block of wood sitting on top of the air track. Okay, and the block of wood, the block of wood is free to glide along this air track because it's like again, like an air hockey table. It's pretty frictionless. What we do is we take a little piece of PVC pipe like this, and we put a nail in the end of it, and we make it into like a little mini blow dart gun. And then what I do is I fire the nail into the block of wood so it sticks like that. And then the block of wood travels down to this position right here. Okay? So what we do is we try to see if this is an example of conservation of momentum, or if momentum is conserved in this example. So let me give you a little bit of data. The equation for an inelastic collision is this. We have M, N stands for nail, velocity of nail, plus mass of wood, velocity of wood. So we have the nail and we have the wood. This is before the explosion, or the collision, I should say. And then after, so after the nail has been fired into the block of wood, we have nail and wood as one object times the new velocity. Okay? So the objective in this one is we typically try to find out what is the velocity of the nail before it embeds into the wood. So setting this whole equation equal to the velocity of the nail, you can follow along here too if you'd like. Pause it and follow along. But we're going to have N plus W times velocity of new minus, we're going to get this whole term over here. We're going to subtract that over to this side because it was added on the left. We're going to subtract it on the right. We have MW, VW. And then we have to get rid of this MN, the mass of the nail, by dividing this whole thing by the mass of the nail. Okay? Now, some of you may be already thinking ahead and saying, isn't this 0? Because it's sitting at rest here. It hasn't moved yet, right? So this whole thing over here is really, I'll just put a little, it's 0, or you could say at rest. Okay, we can eliminate that whole thing. So let me give you some numbers. The mass of our nail, let's see, I have it written down here, was 4.5 grams. The mass of our block of wood was 355 grams. And then we divide it by 4.5 grams. That's the mass of the nail. Okay? The velocity, we have the velocity of our new right here. The data that we collected in class, so if we would have done this, we do a 1 meter distance, and it takes that 1 meter distance, and it takes what did I write down? 2.5 seconds, I believe, to get there. Sorry, I'm not very good at the pen yet here. So we have 1 divided by 2.5, and that is 1 divided by 2.5. I believe it's 0.4, but let me just double check. Yes, it's 0.4. So that means right here our velocity is 0.4. Okay? So this right here is what I just calculated. All right, so if you go ahead and do this math, I have 355 plus 4.5. So 355 plus 4.5. I get 359.5 times 0.4 divided by 4.5. So 359.5 times 0.4 is 143 divided by 4.5. Let's see, 143.8 divided by 4.5. I get 31.9. So my final answer is 31.9. Okay? So the question I usually ask then is, does this prove to you that momentum is conserved? And some of you might say, yeah, okay, that it doesn't really prove anything. It just, I give you the equation and you can solve for an unknown variable. That's all it really does. But there could be some logic to it. If you remember back to our blow dart quiz that we took on the projectile motion experiment, our answers for that was about our velocity, our muzzle velocity of our nail was around 50, 45 to 50, depending on your class period, 45 to 50 meters per second. This is 31 meters per second. Well, the nail is considerably heavier than the little blow dart was. Now I probably blew into this a little bit harder to get it to embed into the nail, etc. So it kind of makes sense that it should be less than 40 something, which is what our blow dart was. So there's some logic to it, but this is taking an inelastic collision equation. That's this equation right here for conservation of momentum. The left hand is before the explosion or collision. The right side is afterwards. And then you can use that to solve for any unknown variable. Okay, you'll have a couple of examples like that on your workbook assignment. I would specifically focus on workbook question number 9, the football example. That's a really good one. And that'll set you up well for the test on Friday. Remember, tests on Friday is going to be given between 9:30 and 3:30. That's when the test will be open. You don't have to take it during your hour, but has to be taken during that hour. And you have a 2-hour window. So once you log on, you have 2 hours to finish that test. Okay? If you have any questions, I will be in my office at office hours. Here's my office and my nice room above my garage. Stop by during your office hour or any other office hour, the last 30 minutes of each class period, and ask questions about any of these examples we're going over today. Workbook questions, textbook questions, whatever you have. I'm here to help. Hope you're doing well, everybody. Take care.